Hey, calculus folks, I'm excited for you. This is kind of our first rule that we can follow to calculate a derivative. So it's called the power rule. Right up here in our objective, it says, I can calculate a derivative or I can use the power rule to find an equation for the derivative. Now, you might say, like, why is he saying equation for the derivative? Remember what we were doing yesterday? We were finding a numerical derivative graphically. We were having Desmos kind of magically calculate the slope at a point, and then it's graphing that value as a y value at each one of the x values on our graph. And so we're seeing a picture for the derivative, but we're not really getting an equation for the derivative. Now, there was on problem 5 and 6 yesterday a sine function, and we said, hey, that's the cosine function down there. The derivative is the cosine function. But we're going to start with easier functions than trig functions. We're going to start with power functions. Power functions are one where there's an exponent that's a constant. So let me just show you what function we're going to deal with here. It's going to, well, they didn't write it down here. Let me cover that up for just a second. I got to find my pen tool here. Oh no, you're going to be able to see some of the writing. So what I'm saying is, let's say we had the equation y equals x to the fifth power. See, because it's a constant up here in the exponent, this is called a power function. Now, you might look at it and say, well, that's a polynomial, Nelson. It's a fifth degree polynomial. Yeah, you're right. But they also give them the name power functions. And it doesn't have to be an integer up in the exponent. Like in polynomials, it needs to be integers like 5, 4, 3, that kind of thing. It could be 2.7, and it's a power function. So a power function is more general than a polynomial. And we're going to be able to get an equation for the derivative. So like y prime equals. So after I show you this little explanation, then I'll just break it down and say, hey, look, there's going to be a way easier shortcut than doing all the work that I'm about ready to show you. So I wouldn't suggest you write down every step. I want you to sit back and relax and watch my little process here. So we said that there's kind of several ways of thinking about the definition of the derivative. You could put down the limit as x approaches c of f of x minus f of c all over x minus c. That's one way of doing it. Another way is just to make some small adjustment in where you're located. So instead of actually telling people, like this is the new x value I'm going to go to, we're just going to add something to the other x value. In other words, there's going to be some change of x. Now that value that we're putting is often called h. So if I was to make like a little picture of this, and I had some function here and I was at x, if I wanted to go just a little ways over here somewhere, I could say, well, I'm going to go over some small amount, and I'm going to call that amount that I go over h. Now, see, this x plus h is like my c value. It's like my new constant. Instead of calling this c, I'm calling it x plus h. So this value right up here is x plus h comma f of x plus h. And then this one over here is x comma f of x. All right. If I want the slope between those 2 points, here's a little expression which gives us the slope between those 2 points. And I just put in the bubble the limit. So if we look at the limit as well, what happens? Let me zoom in on this. Okay. So this part right here is making the derivative part happen, right? This part over here is just the difference quotient, it's the average value, and then this part is making the instantaneous rate of change happen. So anyways, let's just look at their little example. If we had an x to the fifth equation, and I run it through that expression right over here, right? If I run it through that expression, I'm going to get this new expression right there. I think we need to see that at the same time over there. So, come on, get over here. All right, so they take x plus h and they're going to raise it to the fifth power minus x to the fifth power all over h. Well, I can't evaluate this because I can't stick 0 in for h. I get 0 in the denominator, right? So what I'm going to do is I'm going to simplify. It doesn't look like simplification, right? It's expansion, right? It looks way more complicated now. But here's the deal. Anytime you have a polynomial or a binomial, I should say, and you're going to expand that binomial, it's going to follow Pascal's triangle. Now, I'm not going to get into what that Pascal's triangle is, but there's going to be, obviously an x to the fifth term right out here. And if you'll notice the way the derivative is setting up, there's an x to the fifth term that's going to subtract from it. So every other term that we have in this expression has an h in it. Just look, there's an h there, there's an h there, there's an h there, there's an h there, there's an h there. So when I go down to this next line, they're gonna cancel out. They're going to cancel out the x's. I use the word cancel, but they subtract to zero, right? So x to the fifth minus x to the fifth is zero. But all these other terms have an h in it, which is fantastic. We want that h in there so that we could divide the h into here, into there, into there, into there, into there. And now we're down to this expression, okay? Now think about this for a second. What just happened to the h right here? These h's divide out to 1. And so I end up with 5x to the fourth, and then all of these other terms have an h in them. Now, in the back of my mind, I'm saying, man, I just said Pascal's triangle like in a 10-second just passing here. If I was to make a video on how all of this expanded, just that video alone might take about 15 minutes. So I'm trying to push us along a little bit because we're going to get a rule up here that we can apply. This little proof or this little example may not be the most, illuminating example in the world. So stick with me for a little bit longer, okay? So the h is divided out, and now we have a term that does not have an h in it. So when I stick the 0 into the h's that are over here, all four, how many terms are there? 1, 2, 3, 4. All 4 of those terms are going to 0 because I put a 0 there, a 0 there, a 0 there, and a 0 there. So 0 times anything is 0, right? The only thing left is 5x to the fourth power. So look, when I get down here, the derivative is 5x to the fourth power. Now, yesterday we conjectured a little bit, and we said that the derivative, the numerical derivative, always looked like a polynomial that is a degree 1 less than the degree that we had. So if we had an x to the fifth power, we were conjecturing that we would have an x to the fourth power for the derivative, right? So let's put down x to the fourth. So the degree just got 1 less. Now, there was no way from yesterday's exploration on Desmos and section 3 that we would be able to get the leading coefficient here. But now we're seeing, hey, wait a minute, it's a 5. See that 5 right there? So you might notice that the exponent was 5. I'm sure you do. The 5 up here becomes the new coefficient, if you will. And then you have a degree 1 less, so we subtract 1 from that power. Now it's a little bit more complicated than that. We had a 1 right here for the leading coefficient to start with. So when that 5 came down out front, 5 times 1, it just became a 5 right here. All right, so let's do a quick another example here. I'm going to call this example 2, if we want to call this over here example 1. Let's say I had my function as y equals 7x cubed, okay? Y prime is going to be, why don't you put the video on pause, you take a guess. You could look at the power rule right down here. I'm gonna move that over and expand it a little bit. So video on pause, you try it. All right, thanks. So if I bring the 3 down out front, so I got 3 times 7, 7's still there, that's not going anywhere. Just like the 1 is still here. And then I have x, and then I reduce the power that was a 3, I reduce it by 1, and it becomes a 2. So this is the power rule that I'm trying to demonstrate for you right here. I'm going to move it over just a bit, and we'll try a couple more examples. I was going to put it like right up here in my notes. If notes are organized in such a way that you could put it at the top, probably a good idea. Maybe you want to put it like right underneath the power rule. I'd rather keep things away from the main topic so that when you're flipping back in your math notebook, this will stand out. Oh, I need the power rule. So you could, well, I said you didn't have to copy this example down. So shoot, man, you could just put it right here at the top. You probably have plenty of room. Okay. Now let's think about some other examples here. All right. So I'm going to try example 3 here, and I'm going to make it a little bit more difficult. So example 3 is going to have, well, let's see, how can we make it a little bit more difficult? I could make a coefficient that's a fraction. So let's say I had 3 halves, and then I had x, and let's say we had 2.7 here, okay? So how am I going to deal with that? I want you to try to take the derivative. And by the way, you notice my notation for derivative, I'm just putting a prime down. If this was called f of x, I'd put f prime of x right over here. So how do we do this one? Put it on pause. You try it. All right, welcome back. I'm going to put down 2.7. I move the exponent. I move it out front. It's now a factor, 2.7 times 3/2. This is really awkward, isn't it? And then we've got x, and then if I reduce the power by 1, I get a 1.7, right? Now, this rest of this, arithmetic is kind of up to you. How do you want to do this? You could do it on a calculator. You could say, well, I've got 1 1/2 2.7. That's what 3/2 is, right? So half of 2.7 is 1.35. If I had 2.7 plus 1.35, that would be, I think, 4.05. So my new coefficient's 4.05. I think I did my arithmetic correctly. X to the 1.7, right? You could convert this to a fraction, multiply the two fractions. That's another way of doing it. I'm not too concerned with what your coefficient is, how it's written in what form. But this is the power rule. We're going to practice a whole ton of them today in class. Thanks for sticking with me on this example over here. I hope that you see that this second term right here is the only one that's going to be left, the one that has one h in it. And it is based on Pascal's triangle. So if you want to just stop the video here and start some homework problems, that's totally good. If you want to see what Pascal's triangle is, just keep watching the video. So Pascal's triangle is like this, 1, 1, 1. And then what you do is you take these two here and you add them together. So that's 1, 2, 1. So if I had a binomial like x plus h and I was going to square that, it squares to x squared plus 2xh plus h squared. So these are the coefficients that go in front of x squared, x times h, and h squared. So on the next line down, 1, 3, 3, 1. So if I add the 1 and 2 together, that's where the 3 comes from. So if I was going to take and expand x plus h cubed, it would become x cubed. Let me just write down the powers. X squared h, x h squared, and then it would have an h cubed at the end. And the coefficients are 1, 3, 3, 1. So I put a 1 here, I put a 3 here, I put a 3 there, I put a 1 over here. So you can see that this first term after the h cubed, or after the x cubed, I should say, it is the one that has one single h in it. And you can see how the power went, like the 3 is here and the 2 is there. It's just a result of expanding a binomial. And why are we expanding that binomial? Because the definition right up here has a binomial, an x plus h, and then you're raising it to a power. Now, it's a little more complicated because these are integer powers that Pascal's triangle deals with. But I'm saying the power rule applies to any power. It could be 2.7, could be pi up there in the exponent, right? Pi is a constant. So you could have, let's try one real quick. Example 4. Let's say you had y equals x to the pi power. Okay, so what's the derivative? Put the video on pause. You try. All right, so I got pi x to the pi minus 1. I think I would write it like that for my exponent, because if you start putting a decimal down like 3.14, now you've rounded it. Now you've got an approximation, or if I leave it as irrational numbers, I've got an exact value. So try the homework today. You got to practice a whole bunch of these so you feel comfortable with the power rule. I know you can do it. It hopefully feels kind of more comfortable than just thinking about theory and plotting stuff on Desmos. It feels like we're doing kind of some real math right now. Good luck